Today we are going to do section 6.7 on page 789. That is the Stokes Theorem. Now the Stokes Theorem, it just basically says that Fdr, the integral of Fdr is the same as the double integral of CurlFdS. That is the Stokes Theorem under certain reasonable conditions, such as C, the curve has to be simple closed curve C, and then S is a piecewise smooth oriented surface with a boundary that is the C. Okay, so somehow the integral around the C, the Fdr, is going to be the same as the integral of CurlFdS. And this information is important in the sense that sometimes one of these integrals might be really hard to do for some reason. Then we try to do the other one to make life easier. Okay, so but before we start proving the Stokes theorem, let's first review some of the concepts, such as what is curl anyway, right? Now here's curl. Okay, this is just some definition a screenshot I got from previous pages. The original definition of curl is, as you might remember, is just this thing right. That's about 50 pages ago, and that is a bunch of stuff. Basically, is the del cross f. Okay, you calculate, you use the new determinant as a mnemonic device in order to remember the formula for the curl of f. So curl of f is a vector field. Okay, and so next. And so now that we remember what that is, I want to remind you some of the other stuff because we're going to need it for the proof of Stokes theorem. First, Green theorem, which states when you have the Fdr, remember Green's theorem is only in 2D. Notice F is only on PQ. Okay, so Green's theorem only works on 2D for now. And so anyway, Green's theorem says that the Fdr on 2D, which is P dx plus q dy, happens to be the integral of the area of D. D is the area surrounded by the curve C. Is going to be equal to qx minus py. That's about 100 pages ago. Okay, and so that's that. And there's some information here. Oops, I think I moved the camera. Excuse me. Some quick information is that because the way curl is defined, it just happens that curl f dot k is qx minus py, and therefore the integral on 2D of Fdr can be defined as curl f dot k dA. That's just a quick aside that we won't focus on that much. Now here's what we are going to focus on in this section. That is, what was the Stokes theorem, okay? Something about integral of Fds. What is Fds? Now you notice the S is in boldface, okay? Remember, the ds, the boldface is the same as nds, where the S is not in boldface. In other words, the one in boldface is a surface with a direction, the direction being n. That's why we write it that way to save energy. But but that's what it means. And how do you calculate it? As you might recall, the f dot nds is the same as if you have RV is a parameterization of S. It has a parameter domain that's D. Then you will integrate it like this. You plug RUV into F, and then you take the tangent, right? The cross product. Didn't we do that like last class? It's been a few days that I've been working on Stokes theorem, so I can't even remember for sure. But anyway, we do the cross product, which will give you the answer of TU cross TV and so on. Okay, that is how you do it. This is the scalar function, which is quite similar, but that is how we do this. Now, and then more importantly, here's the formula what we end up doing. The Fdr is equal to this the first equation, P, RT, etc. Okay, I just took a screenshot of things from page 674 and close by. And you can also write it like this, okay, which the book didn't exactly write it like this, but you notice it's exactly the same thing. And don't forget to plug R of t inside. R of t is the parameterization of the curve C. All right, and anyway, so that's what we did for a while. I think back in page around 670. That's like what, more than 100 pages ago. Well, whatever. Okay, this is how we did it. We can also write it like this, which is when we do homework, is often better to do it this way. That is, instead of writing out the dot product, we'll write it individually because that makes it a bit less error prone. Okay, because when I try to do the homework for this section, I try to just directly use this one, and that turns out to be very error prone. If you write it this way, is how the book does it in the examples, and I found that to be indeed superior. Okay, and of course, this equation is also written like this, as p dx, q dy, and r dc. These two are the same thing, because dx is the same as x prime t dt. See, and that is all covered way back when, and I just want to remind you of all the stuff. I don't know why we want to mention this, but that's fine. If f is PQR is conservative, then curl f equal to 0. Okay, quick reminder. And next is if you have how to do chain rule for two independent variables. It's been a while since we've done it, so I want to remind you of it. So say if x is equal to GUV and y equals to HUV are differentiable forms, and c is equal to fxy. Now that means x is represented by two variables, and so is y. They are both represented by u and v. So when you plug stuff in to do the chain rule, here is what happens. Let's see, where did my chain rule go? Okay, now the chain rule then, remember, is you're going to do partial. For example, we're trying to calculate c equal fxy, and you stuff x and y in terms of u and v. So then to do the chain rule, partial z partial u, you will do partial z partial x times partial x partial u, and then partial z partial y. And then, what is that? Why doesn't it say y? The book has a mistake. I didn't notice. It should be y, okay? The second one should be y. I didn't even notice there's a mistake there, but that's partial y. See, partial x and then y. Same thing here. Partial c partial x. Partial x partial v, and then partial y, etc. Okay, like the way chain rule works. Now with that, we are ready to prove the Stokes theorem. So now to prove what was the Stokes theorem? That means the Fdr integrated around some curve is the same as CurlFdS integrated over the whole area, and we're going to prove this relationship holds. Now to do that, first let's look at the page 792, the following page, where we have a graph. Please stare at this graph for a little bit in your book, and notice that there is a surface on top, okay? And the surface has a vector pointing up, is n. And the surface can be parameterized as, described as z equals to gxy. Your book has fxy here, but then it changed to gxy. So we'll go by gxy, okay? It's not f, it's just g. So z equals to gxy, and the surface S casts a shadow on the bottom that is d, that is the domain for parameterization, okay? And so then, S has a boundary around it, and this boundary is called C. And then it's a boundary, its corresponding domain of parameterization also has a boundary, and we'll call that C prime. Okay, now let's go to the previous page and read the description of what I just said. Okay, I think that's basically what they said is we have surface S, which is given as z equals to gy. Remember, f should be g. And then assuming all the regular things like the circle, the area is reasonable, and the function f is reasonable, and everything is reasonable. Okay, no folds, no holes, no nothing. Something like that, and smooth. And anyway, so then we have some function f. Okay, the f is given by PQR, be a vector that has continuous partial derivatives, etc. Okay, that's the end of 791. Please move on to page 792. So then we are going to do is first let's consider f. Okay, I have it written down here. So the first, remember to change f to g. Okay, next f is defined as PQR. Now what does that mean? Remember PQR each has XYZ in it. Okay, and it's just a reminder. And don't mind the red dot. Okay, that's zipped through from the following page, which we will look at in a second. So f is represented by x, y, z, and s is given as z equals to g, x, y. Okay, which means s can be represented as the parametric form is x, y, g, x, y. And I'm missing a parenthesis here, but you get the idea. And let me add the parentheses. So I added the parentheses, so we're all good, right? S equals to x, y, g, x, y. All right, so we're gonna calculate the tangent. So partial t partial x, which is the same as s partial x, and is gonna be 1, 0 gx, right? If you look at this thing right here. And similarly, ty is 0, 1 gy, and then I put it into the cross product to calculate tx by ty, and after some basic algebra, I came up with minus cx minus zy and 1, which is what the book gives as well. And so so next we're doing pretty good. And next we're going to write down what is CurlF.ds. CurlF.ds, we are trying to prove this, okay? But first we'll see what that is. Now what it is this equation right here. Now this equation is CurlF.ds is given by CurlF. This is CurlF, okay? And then this is dot tx, that's the n, right? Is equal to NDA. And I got that from a previous equation, of course, that we saw just a moment earlier, but I want to remind you again. That is, CurlF is defined by this pile of stuff, okay? P, R, something. And then the surface integral is defined as dot, right here, see? The surface integral is defined as dotting the tangents, which is something we did, I think, just the previous section. All right, so that's where I got this thing. So we got this equation right here. So CurlF equals to the dot product, which then if you carry out the dot product, ignore the red dot, and it equals to this thing. Okay, so far so good. We're just writing down the definition. Yeah, if you carry out the dot product, we get here. All right, so far so good. And that is what your book has as well. Now next, we are going to consider the surface G, where the surface on the top, where the surface S, okay, and the top of your book. I'm not going to draw it because it's right here. So let's consider surface S. S is equal to Z equal to GXY, right? And then we are going to parameterize it. And how we're going to do that? So the surface is right here. So the surface is, we're going to parameterize it. And normally we parameterize it as RUV, as we did in the previous section, I think. But this time we're just going to use XY. Okay, so we'll parameterize the surface as X, Y, G, X, Y. The G is the third coordinate, okay, to show how tall, where it is in space. Whereas G, remember, G equal to Z, because originally we defined Z equal to GXY, okay, so G and Z are the same thing, and during this proof, the book will sometimes call it the surface G and sometimes call it Z. You just have to remember, they're the same. And you can call them either one, is fine. So anyway, so we have, next we have C prime. What was C prime? C prime is the shadow. Let's see, we will talk about C. And right, what is that? Okay, we'll talk about C and C prime. Now C is the boundary on the surface, right? And C prime is the boundary of the shadow D. Okay, so as a result, when we parameterize it, then we get, let's see, right here. When we parameterize it, then C prime will be, being that G is equal to X of t, Y of t. Where did I write down G? Let me see. Okay, now let's say we found the parameterization of C prime, that is the boundary of the shadow on the bottom. Then let's call it x of t, y of t. Okay, we don't know what it is yet, but we know we found it. Okay, there's a way to parameterize the shadow's boundary, that is D's boundary. Then C prime, that is the boundary of the shadow, will be represented as xt, yt. And then your book didn't say the third coordinate, but I just added the third one is 0, being that it's on the xy plane. Okay, z equal to 0. So that's the entire parameterization. Now, if that is true, remember g equals to z of xy. So then the original boundary on top, it will be the same thing, except that you plug it in the third component, that is the z position, will be equal to g xt and y of t, because that's where it is, right? It's where g is. So that would be the z component. And then, so that's the parameterization of the curves. Next, let's consider the functions p, q, r. Originally, we said that the function p, q, r is defined as is all the parts of f, right? Specifically, each one is in terms of x, y, z. Now, if we are going to parameterize, then p will be, now we're going to plug everything in. Okay, and the reason p, where p is x of t, y of t, and the z component is g of xt, yt. And the reason for that is we're doing the same thing that we did earlier when we calculate the Fdr, right? You need to plug in r of t, which is the parametric equation. Okay, plug everything in there in order to calculate the Fdr. So that's what we're doing here. We have to plug in, so this is the parameterization, all three of them, okay? And being that this is parameterized as this thing, then we're gonna, P will be plugged in all the stuff. And the same for Q and R. That is the other two components of the function f up here. So that's that. Next, let's consider what is Fdr. We'll follow the old formula. See this line here, Fdr can be written like this. We'll move. Okay, see, Px prime, Qy prime, and Rc prime from A to B of dt. That is, that's our old formula, and we're going to plug it in right here. In fact, we're not plugging nothing. We're just repeating it right here, okay? Because everything is called the same name. Okay, my camera zoomed in. So we have, this is Fdr, where, and next we are going to calculate z, okay? Z is gxy, that's the surface on top, right? And what is C prime of t? C prime of t, we're going to apply the chain rule, okay? C prime of t by the chain rule of one variable, or something. But anyway, so it's partial c partial x dx by dt. Those two things are d's there. Okay, I tried to write partial at first and try to change it to d. That's why I looked that way. But anyway, partial z partial y dy by dt. And that is z prime. So what we're going to do then, we're going to plug everything in. So plugging this thing into this equation, we get, so we have integral from a to b, so px prime t, that's fine. Qy prime of t, that's fine. Our z prime of t, now z prime of t, being that z is dependent on x and y, so c prime of t, you have to plug this, which we just calculated, c prime of t, plug it right into the R formula where c prime t sits. So you get this more stuff, see? Where you just plug that right in here, okay? So far so good, but our equation's getting longer. And then we'll rewrite the formula a little bit. And so that we have rewriting this equation, okay, collecting terms that has x prime in it. Dx by dt in here is x prime, right? So we'll x prime of t. So we collect terms and we get to this point, and y prime. So you do a little bit of collecting. And then next we have, and now at this point, we're going to go backwards. That is, normally we say that the integral of c, okay, equals to dt, okay, some kind of an integral line in, and then we turn it into integral of the numbers with respect to t. We're going to turn it backwards this time. That is dt, we're going to say this is dt, we're going to go back to mean, this means the integral over the curve C of dx dy. Now at this point, notice that we're on 2D, okay? There's only dx dy, there is no dz anymore because of the parameterization. Now anyway, so there's C prime, and we have taken the formula backwards. That is, we have the formula right here, right? This is our, and on this side, this is our formula. We're saying that it equals to this thing, okay? Which is integral of C instead. The C is Fdr. So we're going backwards. And also, well, actually, I should mention that over here. Okay, now this thing is the same as this. So we're going backwards this way. So we're saying that this integral is the same as C p dx plus q dy plus r dz, because dx is x prime dt, okay? And dy is y prime dt, etc. This is all mentioned on page 674, but I just want you to remind you. So we're going backwards and getting the original integral out. All right, so far so good. So we got the original integral, and what were we doing before? We were doing C prime, okay? The one where we have the one on the ground, so to speak. And so we have C prime right. So then we have the original integral back, where we change x prime to dt to just dx, and the same for the dy situation. So we got this thing. Now what is that? That we are going to, this is in 2D, right? Because this is just on the ground, on the xy plane. So this is 2D, and we're going to apply Green's theorem. Now Green's theorem states, as we saw a moment ago, is that when you integral over C of a dx plus b dy, it happens to be the integral of d being the area enclosed in C, of bx minus ay dA. Now let me show you the original Green's theorem, which is right here, okay? Now, see, here's the Green's theorem. And notice that instead of P and Q, I wrote down A and B, just so to avoid confusion, because we already used A and B in our proof earlier. So I call it A and B. Specifically, that chunk is A, okay? The other chunk is B. So we are gonna, so A equals to bx minus ay. So the next thing we're going to do is follow that formula. That is, this is B, okay? We're going to do bx minus ay, where b and a are defined up here. So we'll do bx minus ay. So we're going to take partial derivatives of all that stuff. Now, before we take the partial derivatives, we got to remember what P, Q, and R is. As we mentioned a little earlier, being that we have we're doing parameterization here where z equals to gxy, so we need to plug all that in there in p, q, and r. In other words, p is right now p xt, yt, and z of xt, yt, and so is q and r. Okay, you need to put all that xt, yt, and z of xt, yt in all of them. We're just not writing it out to save energy. Okay, but now we're going to take partial derivatives. We have to remember all the stuff in here. That is, so how do you take partial derivatives of q plus whatever? Well, first, we'll need to do the partial with respect to x, okay, the first chunk, which I will write it down right here. Now, the first chunk equals to, well, first is partial q, partial x, so far so good, okay? And then the next one is, but that's not all, because because q has an x component, and then z also has it has a third coordinate where z also has an x component. So the whole thing added up being, to take partial derivative of q with respect to x, you have to do partial q, partial x, the first one, and then partial q, partial z, partial x by the chain rule. That together will take the partial derivative of just q. That's the first part. Secondly, we're going to do the second part. What about partial q or times partial z, partial y? In that case, we are going to do the product rule. So first, we're going to take the derivative of partial r partial x, which is this pile of stuff, okay? The same as q. See, q partial with respect to x has two things, and same as r. R also has two things because it has a z that has an x in it, base is y, okay? If z has x in it, you have to take partial z partial x as well and multiply it together by the chain rule to work. So that's derivative of the first part, okay, the r part in the product. This is a product right here, times partial z partial y. And then you're going to take the partial c partial y and take the first part, which is r, times derivative of the second. I'm talking about the product rule here. So the derivative of partial c partial y, you take derivative with respect to x, and you get this thing that is a mixed partial, okay, where you have partial squared c and then partial x partial y. So there's all these, oops, sorry. Now, so this might look a bit confusing, but if you stare at it long enough, it will make sense. The main reason we're doing all this is because we have P, Q, R. Each one of them represented by x, y, and then c of x, y. That's why you have to do all these chain rules. And then, of course, there's a product here. In the first chunk, which is whatever that is, and then the second chunk the same way. Okay, they're very similar. So here's the second chunk, and the logic works exactly the same way. That's just with respect to y instead of x. But you write it out exactly the same way, and so now we have two chunks of stuff. Okay, and we have to integrate it. But before we integrate it, let's see if there's let's clean it up a little bit. And you notice, remember, we are subtracting the top chunk. And then by the bottom chunk, right? This subtracted by that. And if that is the case, then some of the terms are identical and we can get rid of it. First, this and this is the same thing because mixed partials are equal, okay? Which is nice, right? If yx and xy, they're the same. So these two subtracts out. Secondly, this thing, the two red dots. Now the two green dots are the same. They are the same thing. If you look at them very carefully, that's partial x, partial c partial x out here, and partial c partial y. They're exactly the same thing. So those two things also cancel, subtract out. So we got rid of 4 things. So we only have 6 things left. Now let's look at the 6 things very carefully and look at the bottom line. Okay, the 6 things when you do the subtraction will end up being this. If you look at it very carefully, is qx minus, what is that? I can't even read it. It's something. Figure it out. Okay, it's qz or something. Well, whatever. No, I think it's qx. Yeah, it's qx because there's only a qx right here. Okay, there's no repetitions. The repetitions are all canceled out. So I mean subtracted out. So you have qx and then ry, or no, that's qz because qx is over here. Okay, and qx minus, and anyway, my point is when you do all this, you come up with this equation right here by the time you sort it out, and that happens to be the same equation as what we found out. What is that? Okay, that is the same as the thing we did a little bit earlier in the proof. It's the same as this equation right here. Okay. And this equation, as we found out, is CurlFdS. See, that's what we calculated a little bit earlier, equal to this thing. And that thing, if you patiently check every single term, you will find out to be exactly this thing right here. And that, what have we been doing? Well, we have started with Fdr, right? And we ended with CurlFdS. And that is the proof of Stokes' theorem. Now that we have proved Stokes' theorem, which states that Fdr is the same as CurlFdS, let's do some examples. Go to page 793. Let's look at example 6.73, which asks you to calculate both Fdr and CurlFdS for this situation and see if they equal. Okay, so please do that. I want to mention one thing. Is the book keeps, in this whole section, the book keeps mentioning follow equation 6.19, but that's not the case. It's actually equation 6.20. Okay, let me show you my screenshots here. As you can see, equation 6.19 is the surface integral. That is the one that isn't a vector. Okay, the one that has vector, which is what we are interested in, is 6.20 and 6.21, which is what we've been doing in the last section, I believe. So that's what you're going to be using to calculate this thing. All right, so so anytime the book says 6.19, it means 6.21, basically. So anyway, now that you know that, so please do that. It's fairly straightforward. The book is it doesn't give you the details of parameterization and how to do the cross product and all that. It just sort of did it. So please supply that yourself, and that should get you to the answer soon. Now the only difference is we have done this. We have done Fdr and we have also done FdS. The difference, however, is that we've never done them together. And the process are similar, right? You take derivative here, you take derivative there, and it's easy to get confused and forget, what am I doing here, right? So when you get confused, then go back to the principle of this. That is, get back to remembering what is going on. That is, this is Fdr and this is F.and ds. Okay, we will be doing this or that or both during this section. So just keep them clear in your mind. If you can't remember what am I doing, then go back and look at this page right here. Maybe even take a screenshot of this page just to be absolutely clear on what we're talking about. All right, because that is going to be needed for doing all your homework, because this entire section is about calculating Fdr or CurlFdS or both. Okay, so so that's example 6.73. Please do that as part of your homework. Next, let's look at example 6.74. But before that, I want to show you something. Now here's the meaning of the significance of the Stokes theorem. Now first, let's consider this. This is a flat surface. Okay, it's round. It's a perfect circle, but you're looking at it from the side. All right. So we have a surface here, which doesn't do anything, right? Now what I want you to do is take the surface, okay, and then push it in like it's made of rubber or Play-Doh or something. So you turn it into a bowl. Now at this point, you got to understand the integral over the surface, that is the bowl-shaped thing, is the same as the integral around the edge of the bowl. Is what the Stokes theorem says that we just proved. That is, they are the same thing. See. The integral of the surface in here, which is a perfect circle, the integral of this one is the same as the integral around the red line, the boundary around it. Okay, so the surface doesn't matter. They both equal to just the boundary. Okay, and the same as if I push the bowl in more, see, it's pretty deep. The surface is becoming quite deep, right? And that doesn't change. This theorem still applies. If you push it deeper, the integral around the surface, that is my deep bowl here, is the same as the integral around its boundary. These three boundaries are the same. You see the red line? Yeah, the three red lines are the same, and therefore you have this thing holds. So it doesn't matter which surface you integrate over, as long as the boundary is the same, the value is the same, is what the Stokes theorem is trying to say. Now I have a fourth surface, as you can see. Look at my fourth surface. I pushed it in a ton, okay? And again, makes no difference. Doesn't matter how far I push it in. The integral still stays the same. That is, the double integral over S of curl F is ds is the same as the line integral around the boundary. Now, if I were to continue to push that surface, okay, which got to become a deeper and deeper bowl, right? I'm talking about this thing. So if you keep pushing it, the bowl gets deeper and deeper, okay? And you can eventually push it to make it look like this. Look at what happened to my bowl. It is extremely deep, okay? It pushes all the way in and it winds around, and doesn't it look repulsive? I think this thing looks pretty repulsive, but doesn't matter how deep it is. Okay, as deep as this is, the Stokes theorem still holds. That is, the integral of that weird surface, okay, over S is just the boundary, okay, the boundary of the opening. See, the opening boundary is just some random just a circle, a regular circle sitting straight up, and the surface doesn't matter. Okay, so that is I got this picture on page 795, which is the example 6.74. Okay, now you have to calculate this thing, which the surface, of course, is way too weird. We can't parameterize it or nothing, but we don't need to. We just calculate the the line integral around the circle, which is its boundary. You think that's the boundary? Yeah. By just because you pushed it in a long ways doesn't mean it's not the boundary. So please, this is example 6.74. That's where I got this repulsive looking thing. Okay, and so please do example 6.74 as part of your homework. Now here's another example of some weird surface. Look at that thing. Okay, now and there's a weird surface. You're supposed to calculate curl f.ds. All you have to do is look at the boundary. The boundary is just where the surface ended. Okay, and that's the boundary, and you just integrate through the line Fdr over C around the boundary, and then you get whatever that is. We don't care how much it bulges out or move around or something. It totally is the same thing. Now with that, let's look at example 6.75. Now example 6.75, we're supposed to calculate the Fdr, except that this time the C, the curve, in the past our C is pretty straightforward, right? It's something on the plane or something similar that's fairly straightforward and easy to parameterize. This one is not as easy, okay? And so I want you to focus on this example because you're gonna need the skills taught here in your homework. Now I have example 6.75 written out. We have so we're supposed to do Fdr, okay, where F is equal to that pile of stuff, and we have our C is made of 4 points. You go around these 4 points, and which the 4 points has a shadow on the xy plane as just the first two coordinates, which is these are the shadows, okay? And in other words, that's how we are going to parameterize these things. Well, necessarily, I don't think it's necessary in this case, because instead of doing Fdr, we're going to apply Stokes theorem and do CurlFdS, which we only care about the area and not the line parameterization. So we only have to parameterize the plane. Now, parameterizing the plane is not as obvious as the book make it sound. Here's how you do it, okay? Now, you have 4 points. You only need 3 points to find the equation of a plane. Now, this plane, as the book gave us, is equal to z equal to 1 minus x minus y. If they didn't give it to us, we could have done it by looking at page 195, where we learned how to find the equation of a plane based on 3 points. We only need 3 points to come up with a plane. Okay, these 4 points happen to be on the plane, which is good. So, but you only need 3. So once we figure out the equation of the plane, which contains all 4 points, then we parameterize it simply as xy, and then let z equals to 1 minus x minus y, where x goes from 0 to 2. Okay, as you can see, the x coordinates going from 0 to 2, and y coordinates go from 0 to 1. See, check here, y coordinates from 0 to 1. And if you do that, that will give you that odd-looking surface. You can also plot this surface into the graphics calculator, but it's probably not that necessary. We'll just do the parameterization that way. So then we calculate Tx, which is S of x, okay, which gives you some kind of a bunch of numbers because it's a plane, so it's just a bunch of numbers, and then do the cross product. And if you don't mess up, you notice that I messed up a little bit there. If you mess up, then you're going to get the wrong answer, then come back and figure out where the mess up is. But eventually I calculated that the Tx cross Ty, and then I calculate the curl of f. Curl of f is up here given, so you calculate curl of f with the determinant notation right here, and then eventually come up with something equals to equals to this. Okay, the minus sign is not on the outside. The book shows the minus sign on the outside, I think, and it's just a slight typographical error. The minus sign is in front of z and is on the inside. Now, having said that, then we're going to do the dot product, okay, which is the curl f over here, dot the tx by ty, which we calculated right here, and then dy dx, and with the endpoints going where we were supposed to. Now, remember, this is what I said. Let's see. What I showed you earlier, that is FDR. The easiest way to calculate FDR, you can go by the equation on top. Let's see, right, the equation on, and give me a second here, let me hold this right. Okay, you can go by this equation, but I find this equation to be easier to do, okay? That is, you take this step first, plugging in the RTs on P, Q, and R, and once you plug it in, then you do this. Then you do the dot product, which is, multiply and then add them together. And that's what we're doing right here. We are doing the dot product, okay? And then, we'll do the dot product, and then we multiply together, stuff together, and which becomes some integration. And if everything looks well, then we end up with the number 3, which is the right answer. So in this, I find that this section, the hardest part is actually parameterizing your surface or your surface or your curve. Okay, once that's done, everything else is similar to what we've done before. And of course, you always have to remember, am I doing integral over C or integral over S? Because it's easy to get confused because we have to do both in this section. But anyway, that marks the end of example 6.75. Please do that as part of your homework as well. Now we have come to the end of the section. Now the rest of the section, you notice your book wants to talk about what curl means. We don't care what curl means. We're math students. This is not a physics class. And as you can see, in fact, in the homework, they don't even mention it, okay, what curl means. So the guy who designed the homework agrees with me. So therefore, let's go do the homework. Now, homework is on page 802. I can't find it. Give me a second here. Okay, please do problems 329, 33, 37, 41. In 41, please do both FDR and CurlFdS. That way you can see if they're equal, because they're supposed to be equal and doesn't hurt to try both, okay? And then 343, 345, again, please do both FDR and CurlFdS. And then and next, and also check example 6.73. I have written down in your notes to figure out how to parameterize stuff. You imitate that trick and then everything will work out. In example 6.73 in parameterizing. And next, 349, 351, 357. And again, 357, please do both FDR and the CurlFdS. And then 361, 365, and 366. Now theoretically, what we are supposed to do one or the other when one's too hard, so we skip to the other. As in doing the homework this section, I have not found the one to be much easier than the others. They seem both hard. But it's a good exercise, see, for you to be extremely good at doing FDR and CurlFdS. Okay, so please do your homework, and when you're done, I want to talk about some of them. Oh wait, I forgot to talk about example 6.73 on page 793, which is let's talk. Sorry about that. Let's talk about that now. I should have written it down. But anyway, example 6.73, which states that now example 6.73, we have a function, okay, and we're supposed to show that FDR equals to CurlFdS. Now to do that, the hardest part is basically the most unfamiliar part that we have is basically parameterizing the surface S. Now S is given equal to z equal to x 4 minus x squared minus y squared. So what we're going to do is just parameterize it just like that, x, y, and then plug z into there, 4 minus x squared y squared. Where x will go from -2 to 2, and notice y. y is going to go from minus 4 minus x squared and 4 minus x squared. That's because we're setting this equation equal to 0, okay, to calculate y in terms of x. That's where this comes from. So if you set that equal to 0, solve for y, you will get this. And y will vary between those two because this is describing a circle, but parameterizing a circle in a slightly different way. Now, once you've done that, then everything comes out very nicely. You calculate, you have s, you go through the motions, right? You calculate tx, ty, take the cross product, calculate curl f, then keep going, take the dot product, and so on, and don't mess up, and then integrate. You notice that when we integrate, we have variables for y, and that's perfectly acceptable, okay? You just plug it in like it is just some number and not a variable, because you're taking the derivative with y first, and then x. So everything will work out. Now, eventually, after you're doing a power integration, okay, remember, the y, you will just plug it in like equal to the bunch of equations. You plug it in like some number. And then you keep going and clean it up a little bit. And one of them equal to 0. Well, anyway, so you end up being like this. Let me see. Well, it equals to 0 just because it got subtracted out. You have two identical things, which is helpful. So you come down to here, and then here, and then so then I eventually plugged it into the integral calculator and came up with minus 4 pi, which is the correct answer. Now the next method is that we're going to do the C Fdr. The Fdr is parameterizing. What we're just parameterizing the C is just the circle on the bottom, which is the boundary of that thing, right? And then that is much better. And so we calculate C prime and follow the formula for Fdr, where we take the dot product of, you plug in F with C, okay? C values go into F, and then you dot C prime. See, that's why this look like that. So once you've done that, then we have, well, we have something, and then also equal to minus 4 pi, and that is good. And then one more thing I want to mention is we did Fdr over C, and we did CurlFdS over S. Now there's a third thing I want to do is instead of going over the original S, how about we just integrate over the surface on the ground? Because as we mentioned before, that integrating over this surface is the same as integrating over this surface, right? So how about we just integrate over this surface? Actually, in our example, we're doing this, right? This is our surface, original surface. How about we integrate over the surface on the ground? Because that's much easier to do, right? It's just a circle. So that's what I did, which your book didn't do, but I thought I'd try that and see what happens. So method 3. Okay, we're going to integrate where the surface is, what's S? S is just x, y, 0, okay? Where x goes from minus 2 to 2, and y goes from minus square root of 2 minus x. Is it 2 minus x? No, it's 4 minus x, sorry. Yeah, I wrote it, but I fixed it later, okay? It's 4 minus x. I should fix it now. But anyway, so we have, the integral is the same as up here where we did 4 minus x. Y goes from one 4 minus x to the other 4 minus x, minus to plus. So the same thing here, except that this is not the surface before. I just integrate over the surface on the ground. That is on the xy plane, but with these limits. Now, as this ranges, right? So that's still a circle. Now with that, we calculate tx, ty. As you can see, these are much easier. And the cross product is just k, because these things are just I and j, and I cross j equals to k. So then we do curl f dot 0, 0, 1, which makes it not, curl f is from, we have done that previously, but in this problem. But if we dot 0, 0, 1, that makes it much easier, right? It just equal to something like this, because you only care about the last thing. So you end up being just minus 1, and then when you integrate over this stuff right here, we get end up being the area of the circle which is just minus 4 pi, which is the same as before, but is fairly simple. Although not a whole lot simpler than this, because you still have to calculate curl F, which is takes work. So generally speaking, I would say that the integrating along the curve is superior. Seems to be easiest way. The others are much longer. Okay, so anyway, so that is the part I forgot to mention. I'm sorry about that. And so please go do your homework. Now that you're done with your homework, let's talk about some of them, or maybe all of them, I don't know. And anyway, first problem 329. We have the function. We're supposed to, in this problem, we're supposed to calculate both the CurlFdS and Fdr. Okay. So let's do that. Numbers, okay, 329. To do that, we have, I have it written down here. Okay, here's the function, which is supposed to calculate both. So we'll do the curlF first, because it's probably harder. So I wrote down curlF by definition, and came out with something like this, which doesn't look too bad, right? And then I did the, for this, I did the sphere, because being that this is a sphere, I did the sphere parameterization, which is probably not the best way, because that's more complicated, and whereas the way your book did, which is simply, well, being there's a sphere, I don't know. It might be hard either way, okay? So maybe that's a reasonable parameterization. But anyway, so I parameterize it from the sphere, copying from page 772 when stuff is already done. And we know what T5 by T theta is. I just copied it all down. And except that the A is different, okay? The radius is 3 instead of, I think it was 2 before. And I forgot about that at one point, so as a result, I got the wrong answer. And then found out that the radius is 3 now, okay? That's a result of copying. Anyway, so I got that, and then I did this integration, did this dot product, okay? So we take curlF and dot this T5 by T theta, and I got this big long thing for integration, which I plugged into the Wolfram calculator, and it gave me the right answer. See, the answer is when you all said and done, it equals to 18 pi. The only mistake I made, but at first it didn't give me the right answer, and I was wondering if there's something wrong with the calculator, and then eventually I realized it's because I was not careful, and I typed in du dv. It should be dv du, because we're integrating v first and then u. See, and you have to be, and I should have been more careful, and that because that's the only way the calculator can tell who are we integrating. So I wasn't paying attention, and so I got the wrong answer at first. But once I typed in the right answer, I mean the right way, when I changed du dv, then as you can see, everything worked out very nicely. And the answer is 18 pi. Now that is just the curlF dot, this part curlF dot ds. The next thing we need to do is, the next thing we'll do is Fdr. Now Fdr is much simpler. As you can see, we have followed the rules of Fdr, where C is just a circle on the ground, so our prime and stuff comes out very nicely. And as long as we plug in everything properly, see, C get plugged into F, okay, and then dot C prime, which is R prime, and then it also end up being 18 pi. So that's great. So that's the end of 329. So next, let's look at problem 333, where we're supposed to calculate this very interesting description, okay? Where the hardest part, as far as I can tell, is to parameterize the curve. Is that, in other words, you have, the description says that your C is comes from the intersection of C equals to x squared plus y squared and Z equals to y. Now to parameterize that, if you set these two equations to be equal, okay, and then you have, you can come up with something like this. So the parameterization equal to square root of t minus t squared. Why don't I have it written down? Well, okay, I got it. So here it is. Now, the way I parameterize it, I let y equal to t and z equal to t, because y and z are the same, right? And then x, well, then if you solve for x, then x squared will be equal to t minus t squared based on this equation. And as a result, x is the square root of it. In fact, x comes in two parts, the positive square root and the negative square root, which gives you two curves of c, c1 and c2, whereas the original c is the combination of those two curves. And as you can see, if we parameterize the c1 and c2 from 0 to 1, then c1 is whatever it is, where c2 is going the wrong way, so to opposite way. So the actual c is equal to c1 minus c2. That the minus just means that c2 is going the other direction if we parameterize both curves from 0 to 1. All right, so then we have the two curves right here. Okay, and then once we have done the parameterization, then the rest is just routine calculation of Fdr. And in this case, we have to do two of them, and then subtract. Now to do two of them, so we do that. First we calculate c prime, that is the derivative, okay? To take the dot product, we have to take the derivative of the curves. And so here's the first one and here's the second one, and they look similar. And then we take the dot product of both, and you notice eventually that the dot product of both things are the same, okay? They are exactly equal, the integral of Fdr over C2 is the same as integral of Fdr over C1. And being that the integral we're looking for is a subtraction of those two identical things, the overall integral equals 0. And that is the right answer. Which, yeah, all this sounds like quite a bit of work, and it is. But, well, that's the way it is when it comes to Stokes Theorem, okay? And basically, no matter which one you do, it's hard. So let's look at the next problem. Oh, I forgot to show you what problem 333 looks like, okay? And because I did graph it, so I want to show it to you, so I didn't just graph it for myself. Take a look at the graphs. If you graph this thing, then you notice that c equal to x squared y squared is the curved surface. It's not curved very much, so it's kind of hard to see. Whereas z equal to y is the flat surface. So this is one angle, and this is the back end, okay? Turn clear around the other side. And then the circles are done by two curves. I don't know if you can see it. One's green and one's purple. But that's the positive and negative curves. And you notice it just goes clear around the border very nicely. So please plot this into decimals if you want to see what it looks like. Next, let's look at problem 337, which is a simple line integral of something over over C, the curve, but the book insists on you using the Stokes theorem, means that you can't do the easy one, you have to do the tough one, okay, the CurlFdS. So that's what we're gonna do. But this one doesn't happen to be too bad. So what we do is we follow the instructions, we calculate what CurlF is right here, and then we calculate t theta, the tangent, the t by t cross t thing, which in this case, I copied it. Being that this is a sphere, I copied this result from page 772 where this stuff is already done. Okay, so we don't have to do it again, which makes this problem slightly more tolerable. So then once we did that, we do the dot product, which end up being two parts of it is 0, so that's good. So we have just this thing here, which end up being minus 2, 3 pi, and that is correct. So that is not so bad. Next, let's look at problem 341, where we have, well, we have something to integrate. What am I doing? It's 341, where we have CurlF, we have to do CurlFdS equal to Fdr, and we will do both. Okay, so what we're doing first is we're going to do the line integral. So we'll do Fdr, and in this case, it's a rectangle. It's a bottom of a upside down box that's opening, right? And so we're going to do the rectangle, which consists of 4 lines, and then then we take the derivative of 4 and calculate all 4 line integrals. And after some mess, and I eventually figured out that equals to 8/3. It looks messy, and it is. But if you get through all this and figure out and not mess up, then this is the answer that you eventually get. Now, and then what I did is, instead of calculating the line integral, we're going to calculate the surface, that is the CurlFdS. But we're not going to do the original surface. The original surface is just a box, right? Like kind of like this, it sticks out. But we're going to do the surface here, that is the opening surface, which is much easier. We're not going to go over the box, but just the surface at the opening of the box that's surrounded by the boundary, because that's flat and easy to parameterize. So that's what I did. Now when I calculate this thing of the surface, okay, where the surface is just, we're integrating, the surface is just uv 0, that's it. Okay, and where u and v are both from -1 to 1, so then the cross product is just k, 0, 0, 1. And which means that being that you're crossing this thing with just k, you only have to do the last component, which it happens to be qx minus py, which is this thing, and then we integrate it. It quickly gives us 8/3, same answer. So it's much better. Now let me hold this, maybe hold this a little better so you can see it, what I did, and that is the problem. So as you can see, Stokes theorem works for problem 341. Next, let's look at problem 343. We have a whole bunch of lines, actually just 3 lines, okay? So we have 3 lines to integrate over, so we'll do Fdr, and then, so we parameterize the 3 lines like this, and take the derivative, and the next job is just simply integrating over each line, and then add it all up or something, okay? This is, I made some mess here, but eventually I did get the right answer, see, right here. So after you integrate all 3 things, and you add them together or something, and then end up with -1/6, and that is the right answer. So I'll let you see this one more time. It's kind of a mess, but that happens. But anyway, you can probably make some sense out of it. Next, let's look at problem 345. Oh, I did not write that down. Okay. So 345, we are supposed to use the Stokes method to make things harder, okay? Because using just the good old, just doing Fdr, which is what we're trying to look for, is fairly straightforward. So I did the Fdr method first, the easy way, and then we'll do the CurlFdS later. Now here's Fdr. We have that surface. And the hardest part, as always, is the parameterization, where c equals to 2 parts, c1 and c2. You do the subtraction, where you solve for where x, if you set x equal to t, and y equal to, z equal to 1 minus t, because of this relationship up here, then you solve for y, and you end up y equal to plus or minus that square root thing. And then from there, you have able to come up with a parameterization of the 2 curves, both of which go from 0 to 1. And then you can, from this point on, everything is routine. You calculate c prime, take the dot product, plug in the right things, and then eventually come up with some kind of answer, which is correct. Okay, that is the easy way, which is not what the book wants us to do. Now, so we're going to do the hard way, where I need to find it. Okay, the hard way is using the doing CurlFdS, ds, which is fine. We can, to do the parameterization, I do the same trick that's pulled by example 6.73, okay? So what we're going to do is we have the same curves here, and we are going to parameterize it as x. The surface will be called s, x, y, and 1 over x. The trick, however, is in the boundary, okay? That is, x is going from 0 to 1. See, here's the boundary of this thing. And whereas y, you plug y into the equation, and then solve for y, plug not y into the equation, but the situation into the equation, okay? And then you solve for y by putting these two equations together, and eventually you get y equals to this, plus or minus square root of x minus x squared. So once you get that, then we are in business, okay? And then so the hard part is just to figure out what the limits are. That is, what's y ranging from? So y is ranging from positive and negative of the square root of x minus x squared. Once we figure that out, then the rest is routine. You calculate curl of f, calculate tx and ty, which is simple because s is just some plane. So tx and ty is some kind of some numbers, and then the cross product is 1, 0, 1, and then you take the dot, you dot the curl f with the cross product, and then do the integration. Okay, remember the integration is x minus x squared, and eventually you get the same answer of pi equals to answer of minus pi over 4. Now, the hard part really in this section is just getting the parameterization right. So next, let's do problem 349, which is a kind of an unusual problem, but otherwise it's similar deal. We have the surface. I mean, this is the equation we're trying to get. You might wonder, what does that mean? That the FDS will interpret it as, if the book says that means the same thing as curl f dot ds. Okay, that's how we're going to understand it, because the book didn't really explain, and that does give us the right answer. So here's the definition, in case you're wondering what are we doing here. So FDS over C is the same as calculating curl f dot ds. That is how we understand that term to mean. All right, so here's what we are given. We have the surfaces on this side, the intersection, and then we have, so we are going to do that, okay? So the function, the vector function, we'll define it as this way, which means the surface, which comes from here, I'll define it like this, x, y, and then 1 minus, the z is just 1 minus 2x, 2y. Okay, but what are the limits? The limits are x goes from minus 1 to 1, and then y will be solved from here. Okay, y will be 1 minus x squared, take the square root from negative to positive. So that's how I'm going to do that. And so now that I got the surface and I know what this means we're going to calculate curl f dot ds. We are going to do the curl f dot ds, all right, and which is that thing. Okay, and then from then on, it's just doing same thing we've always done, okay, and do the integration, and it came up to 2c pi, and that is the answer at the back of the book. So that's that. Now, problem 351 is give us an easy problem so that we can relax a little bit. What happens is we're doing the same thing, okay. We first we'll do curl f dot ds. So we go through the motions and get through what curl f is, and then the surface is just x, y, 0, but we are going to, I haven't calculated the limits for it yet, okay, because we're just doing the surface on the ground. No matter what, this is actually a sphere, but we're going to calculate the surface on the ground, and which is just a circle. And but it's on the plane, okay? And I haven't calculated the limits yet. All I know is that the tangent, cross product is 0, 0, k. Now at that point, you notice that everything sort of end up being 0, okay? The integrand end up being 0 because you're dotting 0, 0, k, and curl f, well, whatever it is, it end up being 0, which is it? Let me check. Yeah, I should trust myself, okay? I did check when I did the homework, and it is 0. Trust me, when you plug everything in just right. So then so the whole thing is 0. I don't even have to integrate it. So then I redid this problem by doing FDR. See, before we did curl FDS, right? Now I do FDR, which tends to be shorter because we're doing around some circle, and then that also come out to be 0. So, and that is the correct answer. All right, next let's look at problem 357, where we have doing the same thing. We have curl f ds, is the first thing we're going to calculate. But before that, we have to parameterize the surface, which is always the most confusing part. But the surface is given by x plus c equal to 5 and x squared plus y squared equal to 9. So we'll describe the surface as xy, okay, and 5 minus x, which is z. And then we'll solve for y. X goes from minus 3 to 3, and y is the square root of 9 minus x squared. Okay, just solve for y, and you get this. And that's our parameterization. Now, once that's done, then everything is follow the recipe. Okay, we'll calculate f, curl f, right? And then calculate sx, x, sy, for the surface. Take the cross product, and then calculate the integral, and hope that everything comes out and not mess up. And then look, yeah. And then eventually I got this, which is the correct answer. So that's the curl FdS. And then next I calculated Fdr for the same problem, which is much easier, as you can see, where C is this thing. Yeah, why I see this thing? Well, because I let x equal to 3 cosine t, y equal to 3 sine t, and then z is 5 minus x, okay? Which, as you can see, 5 minus x. And then everything else falls out nicely. And this is much faster. Yeah, anyway, I also get minus 36 pi. All right, so that's 357. Next, let's do problem 361, where we have a line integral, but we're forced to do curl f ds, which s is the surface, which is the circle. It is a circle where where z equal to 1. So the hardest part is always to parameterize the surface. So the parameterization is as we'll use u and v. Okay, so s will be u cosine v, u sine v, and 1, because it's a circle but with the height 1. It's not on the xy plane. And then we calculate. So once we've done the parameterization, the rest comes out, right? We calculate su, sv, curl f, su cross sv, curl f dot ds, which is the dot product of those things, and then do integration, and it end up being this part happens to be 0. Because cosine of integral from 0 to 2 pi is 0, so the whole thing just end up being 0. So that's that. I also decided to do 365, and then which happened to be similar to the problem we just did, which is 361. So it goes pretty fast, okay? And that's 365. We have the sphere, which is not a sphere, it's a ellipsoid or something, this thing up here. But however, it intersects the ground as a sphere, so that's good, okay? So we're gonna do curl, and we're forced to do this, I think. And then we calculate curl f, and then s, we do it just like the previous problem, which means that we can just copy this from the previous problem, okay? The tangent, the cross product of the tangents. Then we can calculate everything, and it happens to be 0, because you're dotting 0, 0. The first two are 0. The last one is u, whereas the curl, the last item on curl is, well, it ended up being 0. Anyway, so that is problem 365. Problem 366 is the same as problem 365, except that you're doing the Fdr instead. So which is much easier usually. So we'll do the Fdr, which is f, okay, dot dr, as you can see, is also equal to 0, being that they are the same problem. We're just doing it as a different way. And with that, we have finally come to the end of the Stokes Theorem section.